Lesson 4.2 are real zeros of polynomial functions. So the real zeros of a polynomial function are the roots or zeros of a polynomial function which exists in the real number system, so not imaginary numbers. A polynomial cannot have more real zeros than its degree. The remainder theorem says that if you have a polynomial function f of x and you divide it by x minus c, then its remainder with that division is equivalent to your function valued at x equals c. There's a little proof there that kind of shows it, but basically whatever you end up with is exactly the same thing as if you were to find the y value at that x value. The factor theorem says that x minus c is a factor of a polynomial if and only if f of c is equal to 0. So you know something is a factor, then you know its y coordinate is 0. If you know its y coordinate is 0, then you know it's a factor. If f of x is a polynomial and f of c equals 0, then you know that x equals c is a 0 root x-intercept of f of x. You also know that x minus c is a solution, or excuse me, x equals c is a solution to f of x equals 0. You also know that if you divided f of x by x minus c, it has to have a remainder of 0 based on the remainder theorem. And you also know that x minus c is a factor of f of x. So all of those are interchangeable. If you know one of them, then you know all the rest of them as well. So we want to find p of 2 using the remainder theorem for p of x equals 3x to the fourth plus x cubed minus 4x squared minus 6x plus 2. So if I'm using the remainder theorem, I'm using the idea that if I divide this by x minus 2, whatever the remainder is the same as the y value. So I'm going to use synthetic division to figure out what my y value is. So using synthetic division, I put 2 in our little box, and then I put my coefficients out for p of x. I brought down the first 3, multiplied it by 2, I got 6, added to 1, got 7, multiplied by 2, you get 14, add to negative 4 is 10, multiplied by 2, you get 20, add to negative 6 is 14, 2 times 14 is 28, plus 9 is 37. Since this was an x to the fourth, this would be x cubed, x squared, x, your constant term, which means your remainder is 37. So therefore, by the remainder theorem, p of 2 would be 37. So for the next one, given p of x equals x cubed minus 4x squared minus 5, same thing, use the remainder theorem to find p of negative 2. So I put negative 2 in the box, my coefficients 1, negative 4, 0 x's, negative 5, brought down the 1, negative 2 times 1 is negative 2, plus negative 4 is negative 6, times negative 2 is 12, plus 0 is 12, times negative 2 is negative 24, plus negative 5 is negative 29. Since this was an x cubed, this will be x squared, x, constant term, and then my remainder is negative 29. So p of negative 29, p of negative 2 is negative 29. Now you're probably wondering, that's really not that much easier than just plugging in negative 2. It's more like if you have done this already, you can also determine what the y coordinate is. You wouldn't necessarily use this specifically to find the y coordinate. Our rational roots or zeros are the roots or zeros of the polynomials that are rational numbers, so fractions or integers. There is a theorem called the rational roots theorem that we use to help us solve for the rational roots of a polynomial function. So we call our first set of values that we're going to find our p-values, which is all of the positive and negative factors of our constant term, so the term at the end with no x. Our q's are all of our positive and negative factors of our leading coefficient. So then we have all of our possible rational zeros of the polynomial functions are going to be all of the combinations of all of the p's divided by all of the q's. So basically what you're going to do is you're going to take your infinite number of possible rational roots and then use this rational roots theorem to limit to a possible set number of rational roots, and then we're going to guess and check until we figure out which ones are actually rational roots for the polynomial. Another thing that's useful to find is the intermediate value theorem, which says that if you have a continuous function, which all polynomials are continuous functions, and you have an x coordinate a that's less than an x coordinate b, then if f of a and f of b, the y coordinates, are opposite signs, one's positive and one's negative, then you have to have at least one 0 in between them. So if you go from positive to negative or negative to positive, you have to cross 0 in between. So what does this look like? Well, if we're given the polynomial f of x equals 2x cubed minus 11x squared plus 10x plus 8, First thing we're going to do is we are going to use the rational roots theorem to list out all of the possible rational zeros. So P is the period, it comes at the end of the sentence, so it's going to be all of the positive and negative factors of your constant term 8, so plus or minus 1, 2, 4, and 8. Q sounds like coefficient, kind of, so it's your leading coefficient, so all of the factors positive and negative of 2, so plus or minus 1 and plus or minus 2. So our possible rational zeros are all of our P's divided by all of our Q's. So if we take each of these values and we divide them by 1, we're just going to get that same list again. So I usually just write P to indicate these same values. Then I'm going to take all of these values and divide them by 2. So 1 divided by 2 is 1/2. 2 divided by 2 is 1. We already have that one written, so I'm not going to write it again. 4 divided by 2 is 2. We already have that one written, so I'm not going to write it again. And 8 divided by 2 is 4, and we already have that one written, so not going to write it again. So what we've done is we've taken an infinite number of possible rational numbers and reduced it down to a list of 10. 1, 2, 4, 8, and 1/2 plus or minus. That could possibly be our rational zero. So if our polynomial has a rational zero, it has to be in this list. So now what I'm going to do is I'm going to plug in -1, 0, and 1 because those are easy numbers just to plug in and evaluate to see what they give me. So when you plug in -1, all of your powers of x that are odd, those coefficients are going to change signs, and anything that's even is going to stay the same sign. So it becomes -2, -11, -10, plus 8, you end up with -15. When I plug in 0, you just get the constant on the end, so you get 8. And then if I plug in 1, all of my powers of x just become 1, so it just becomes your coefficients. So 2 minus 11 plus 10 plus 8, so you get 9. So although none of these were zeros, so I can reduce 1 and -1 as possibilities, it did give me some other information. It gave me something with the intermediate value theorem. So what I noticed is that x equals -1 has a negative y coordinate, and x equals 0 has a positive y coordinate, which means that somewhere in between these two, there has to be a 0. It could be irrational, but I'm going to go with the assumption that it possibly is a rational 0. So I'm going to use the intermediate value theorem to guess that x equals -1/2. If I go over to my list here, x equals -1/2, because that's between -1 and 0, is going to be a rational 0. So then I'm going to use that with synthetic division and test to see if I get a factor. So I plugged in x equals -1/2 into my synthetic division. I did my synthetic division and I got my remainder to be 0. So using the factor theorem, that means that x equals -1/2 has to be a 0 of my polynomial. So we've now found one of our zeros, and we have at most 3 possible rational zeros. But the nice thing is we've now reduced our polynomial down to a quadratic. And I know how to do quadratics in ways that are not the rational roots theorem, so I'm just going to solve this quadratic for my other 2 zeros like I would if I just were given a quadratic. So I solved this thing by factoring. 2x squared minus 12x plus 16 equals 0. I factored out a 2. I'm left with x squared minus 6x plus 8, which factors into x minus 2 times x minus 4. So my other 2 zeros would be x equals 2 and x equals 4. So the 3 rational zeros for this polynomial are x equals -1/2, 2, and 4. So I used the rational roots theorem to find my p's and q's, and my p divided by q's, which are all my possible rational zeros. I then picked easy numbers just to really quick plug in that I can do in my head to see if maybe 1 or -1 works. Neither of them did, but I got an intermediate value theorem where I had a negative y coordinate and a positive y coordinate, which means I have to have a 0 in between. So I went to my list of possible rational zeros. I picked the one that is in between -1 and 0, -1/2. I tested it, and it worked. And then I found my other rational zeros by factoring, solving this quadratic that was left over. Let's say you had more than one, like -1/2 and -3/4 or something like that. You just have to pick and guess and check. So here's another one. F of x equals 2x cubed plus 11x squared minus 7x minus 6. So start by making your rational roots theorem and then step your way through to see if you can find your rational roots for this polynomial. So for my p's and q's, p is the period it comes at the end of the sentence, so it's all the factors of -6, so plus or minus 1, 2, 3, and 6. Q is for coefficient, so it's my leading coefficient, plus or minus 1 and 2. So my possible rational zeros are all of my p's divided by all of my q's. So when I divide them all by 1, I get just the original list back, and then when I divide them by 2, my new extra ones are 1/2 plus or minus 1/2 and plus or minus 3/2. So when I test -1, 1, and 1, for -1 I get -2 plus 11 plus 7 minus 6, so I get positive 10. For f of 0 I get -6, and then for f of 1 I get 0. Yay! This is always a great thing when one of these works. I also noticed that I do have a positive to a negative, so I do have an intermediate value theorem here, so I could go to my list and pick the x coordinates that are between -1 and 0, but I already know one of them, so I'm just going to use f of 1. So I used my x equals 1 in my synthetic division since I knew that was going to work. And I set up my synthetic division, brought down the 2. 2 times 1 is 2, plus 11 is 13, times 1 is 13, plus -7 is 6, times 1 is 6, minus 6 is 0. So yay, it is a factor, which we already knew. But I was really trying to get this quadratic here that's been reduced. So now I can solve this the way I already know how to solve quadratics, which is by factoring. And this does factor, and I get x equals -1/2 and x equals -6. We kind of assumed the -1/2 would work because of the intermediate value theorem here, and it did. So if you had chosen that one to start, you would have gotten the same values, x equals 1, -1/2, and -6. On this one, we're going to kind of take everything we've talked about and put it together. So we're going to use the rational roots theorem and everything we've just been doing to find our rational roots. And then once we have those, we know the zeros, we can actually work backwards to write this in factored form. Because before, if it wasn't one of the ways we knew how to do it, we would not be able to factor it. Now we can actually factor it by finding the zeros first. Then once we have that, using what we talked about in 4.1, we're going to graph this function. So I used my factor theorem and my remainder theorem and everything to find my zeros. When I did this test thing, I ended up with -1 working, yay. So I plugged this in my synthetic division, and I got, yay, it didn't really work. So when you get to here, what we'll notice on this one is this is an x to the 4th. So when we reduce it down, it's an x cubed. So you have to look at it. If it factors by grouping, you can go on and factor this and keep going. This one happened to factor by grouping, so I just factored this and solved for my remaining zeros. If it did not factor by grouping, you would take this reduced polynomial and keep looking at your p's and q's and see if you can basically guess and check until you find another one. So in this case, it factored by grouping, so I factored it and I found that my other two zeros were 2 and -2. I noticed that this factor of x minus 2 shows up twice, so that indicates that that actually has a multiplicity of 2 because it showed up in 2 different places. So now I can take those zeros and I can write this in factored form. So if I have a 0 of x equals -1, then I have a factor of x plus 1. If I have a 0 of x equals 2, that means I have a factor of x minus 2, and since it showed up twice, it's a multiplicity of 2, so it's going to be squared. And then x equals -2 means I have a factor of x plus 2. So now I can do what we did in 4.1 and actually graph this polynomial. And so looking at this, I know my zeros are x equals -1 with a multiplicity of 1, so that means it's going to cross, x equals 2 with a multiplicity of 2, so that means it's going to touch, and x equals -2 with a multiplicity of 1, which means it's going to cross. I know my y-intercept, I've already found that up here, is 8, and my in behavior, my a value is 1, so it's positive, and my degree is even, so as x approaches either positive or negative infinity, y will approach positive infinity. So I have my zeros, I have my y-intercept, I'm going to start up in the positives, cross at -2, cross at -1, and just touch at +2 and end again in the positives.